Hi there, back again to have another look at my RTB2004. This time I thought to do a short video on looking at the logic analyzer part of the RTB and the logic probes, which are the RT-ZL03s. At the moment I've got set up a signal coming out of a GPS receiver which is sitting on top of the BK Precision power supply, and then over to the right I've got a analog discovery device which I use just when I want to inject signals into an FPGA. I've been working recently on doing some work with FPGAs and developing some let's say software, but it's not really software, it's hardware actually, but VHDL language coding for that, and I've been using the analog discovery to work with that so that I can put signals in and check responses, etc. But this also gives me an idea. It also gave me an idea to set this up as a little experiment, just to show the quality of the logic analyzer probes and the logic analyzer input on the scope. But also I thought I would show just with some other data coming in from the GPS, so that we can see it just analysing a UART data coming straight in off a GPS, which is what it's showing on the screen at the moment. I'll come in for a close-up of the of all the items, and then we're going to go to a screen software so we can see the actual analysing. It'll be easier if I use screen capture software and use the built-in software for that. So you can see here my analog discovery with a BNC adapter board that's coming out of it to the left. I've got the channel 1 probe going into a BNC so that we can look at waveforms from the analog discovery. I've also got connected in on that same BNC, I've clipped in at the back, feeds straight into the RT-ZL03 so that we can compare the signals that come in on the analog channel and also on the digital channel on the scope. Over to the left is actually the RT-ZL03 probe. I've only got one of these plugged in. Obviously the scope, normally when you buy this option, it has 2 sets of 8, so each of these RT-ZL3s has 2 sets of 8 logics signals that you can input, plus or minus 40 volt peak to peak. What's also useful with these probes is that you can actually take the wires, which I hadn't realised until recently, you can actually take the leads off, so that if you're getting any additional noise or coupling, you can actually, the leads actually come out the end, which I'll show in a moment, which I didn't realise initially, mainly just for the purpose of stopping coupling, I suppose. The other thing is they are listed at 100 k ohms, 4 picofarads, the loading, and the loading is actually, I measured it to see, because it wasn't affecting my circuit, but I just wanted to see what the loading was, and in actual fact I measured it not using a 4-wire measure but just using a 2-wire resistance measure, and I got about 102 k ohms, so it's quite impressive that they seem to be dead up to spec, and you'll see the sort of quality you get from this. I'll just come over now and show you the other part that I've got connected, which is the GPS receiver. Situated on the top of the BK Precision power supply is the GPS module, which is sending out a UART signal, which is going straight into the logic analyzer of the RTB2004. This was just a cheap £20 in the UK GPS module with an electronic compass. I think they're normally used for drones. I don't have a drone, but I believe these are normally purchased for people building model aircraft, remote control model aircraft or drones. I just bought this, just wanted to analyse some UART signals, and I'm also doing some work with something that I need to log some GPS data, so this was just the easiest and cheapest method to log that sort of data. But it makes a good example of feeding this into the RTB2004, so we'll have a look at that shortly on the screen capture software. Thought it'd be worth taking a quick look at the probes removed from the front of the RT-ZL03 logic probe. What you can see here is the front of the probe. You've got, just where my finger is, you've got the inputs, which normally is where all the connectors would be, and over here I've got the connector, one removed, where you've got the 2 pins that plug into the front, and then the other end of it which is used for sensing, which then has a clip that goes onto it, a easy hook that goes on, and you get a quantity of easy hooks with the item. I think there's 16 easy hooks that come with it. This actual end of the probe has got a resistor in it, so it's which I believe is to do with capacitive coupling, so it's a very similar setup to how you have a 10-to-1 probe set up. So it's more than just a wire, and when you actually measure between the points, you've also got a ground lead on it, so you've got, this is your positive, and then you've also got a ground lead which plugs in, so they're removable ground, and each one has its own ground lead, and you get 16 ground leads, I think actually 18 because you get 2 spare as well, but you get a little ground lead that looks like that just plugs in to the end of that, so that you can then ground it. It's actually a very nice setup, and also the wires being removable do mean that if they get damaged they can be replaced, which I must admit is one thing that worries me on my Keysight scope. The wiring harness I don't think is replaceable, and that's about £1,000 with the software, but I think you have to only buy it as a complete unit, whereas with these it would appear that if you did damage or cut one of these wires, or it got damaged over time, you'd obviously be able to get spares, no doubt. Plus also you can remove them, as I said before, that if you've got any coupling happening and you're getting any rogue signals because you've got wires all sitting next to each other, you can just unplug the ones that you don't need. So it's quite a nice little setup actually, and so far I've been extremely impressed with the signals that can be analysed with this with the RT-ZL3 logic probes. But let's now have a look at the software, and we'll see how that looks on the screen. If we go into the UART setup and we have a look at the menu for bus 1, which is highlighted, so come into bus 1. If we look at the trigger, I'm triggering presently at the frame start, which is why we're getting this trigger point here, which I've got on the left of the screen, starting at the string here. If I wanted to actually trigger, say, on the G here, we would be needing 47 hex to trigger. So if I go to trigger setup, I go down, select, instead of frame start, I go down to select symbol. Sorry, not symbol, beg your pardon. Go down to select any symbol, and 47 is input there, and that's why I've got the 2 buses, because this will only accept a hexadecimal or a decimal value, sorry, hexadecimal or a binary value. You can't put an ASCII value in, which is a slight shame. It would be nice if you also had an ASCII box here if you were displaying in ASCII, but obviously you can't. If I then go back out, we'll now see that the trigger point has moved across to that point there. So that's altered the trigger position there. Still triggering, but it's altered to move on to that. We can actually trigger on an offset from the start of the data, and if we go on to trigger setup and select symbol number, I think it is. Yep, it asks us for symbol offset. If I highlight that, that will now allow me to adjust it with this button over here in the analysis section. If I close this down, I can now bring this back, and you'll see the number, symbol number. If I go to, say, symbol number 4, we should now see, if I alter my horizontal position and bring my timescale back down a bit, we'll see now that we're actually triggering on the 4th one, so the trigger point here is lined up with the 4th symbol. I think that will still be, yeah, no, it's not actually got it. I've lost that position because I've come out of that. But if I go into trigger again, click on that again, I can also click on it to enter it as a number. So if I want to trigger on, say, position 12, I can just go 12, and you can go from a minimum of simple number 0 all the way through to 4095. That is the maximum number. If I go enter there, close that down, alter the scale slightly. Actually, let's bring that across there and alter the scale slightly. You'll see now, it's probably easier to do it by bringing that up a little bit and then bringing this across the screen slightly. We should now be, I think, on the 12th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we are on the 12th where the trigger position is here on the 12th symbol. So I think the signal path had trouble getting this, he was looking at some data coming up on Arduino, and I think he had trouble getting it to trigger for some reason on a specific item. I've never found that to be a problem. I mean, today I'm just looking here at data coming out of a GPS model in UART, but I've used this with I2C and also with CAN bus, and I've not found any actual problems at all with that so far. Everything I've tried to decode with this has worked, and also the trigger position has worked. There's other trigger options, so if we go into the trigger menu, go into menu again and look at trigger, you've got a whole variety of ways of triggering: the start bit, the frame start, the stop bit error, sorry, going off, a breakpoint, a pattern, so you can actually select a pattern of bits that you want to trigger on, or any symbol, which is what I was just doing before. So I didn't click properly. Any symbol. So we're now there. So if I want to change that again, and I want to trigger, say, on say 34. Let's just see what happens if I do 34. Bring that over across, so I had that out. 34 hex. Do that. We should now be triggering, and you can see that trigger point there is on 34 hex. So it's instantly found that, and that's obviously the first occurrence of 34 hex in the data, which would appear to be 4 in ASCII. Okay, so that's the reason I've struck that's the decode coming straight out of the logic probes. What I was saying about the two decodes, that I tend to use two decodes like that if I want to have a look, if I've got ASCII data, and obviously not always, you haven't always got ASCII data, but you might want to use it for problem sorting, so you might want to send some ASCII data out of a microcontroller, but you might also want to have some data coming out in hexadecimal. You can run both decodes, one on top of the other, which I find actually very useful, so that I can see one in ASCII and one in hexadecimal. You have got other display options, so when you go to your display option here, go to bus here, go to menu, when you go to display setup, you will actually also be able to see, you can do it in binary, so this has changed to binary, hexadecimal, decimal with a D after it, octal, and then ASCII. And that's on, and that also allows you to put bits on, so that's clean decode, so you don't have your bits at the top. If I click on that, then we've got our bits showing at the top there, and you can have that switched on each decode. So for instance, I've got it on this one on the ASCII, I've got the bits showing, but I didn't bother on that. But if I wanted to, all I would do is I would go back down to here, select bus 2, go to menu, so I'm now in bus 2 menu, which you can select from here as well. But if I go back, menu, you can select bus 1 or bus 2 there, it takes you straight into bus 1. We want to go into bus 2, so if we go there, click on bus 2, go to menu, I can then go into display setup, and my bits are off here, so I'm showing in hexadecimal. If I click on that, you can see now the bits are showing at the top again. If I click off on that, the bits have disappeared. So that's quite nice. But often I have the bits showing on one and not showing on the other, just so that I can, I don't really need to see both. If I'm showing one in ASCII and one in hexadecimal, it's pointless seeing both. And then obviously up here you've got your actual digital logic signal, which you can obviously position. And the other beauty with this, which again you can't do on the Keysight, you can move any of these around. So if you wanted to have bus 1 above, I can have it up there. I can bring my data signal down to there, so my bit pattern stream there, and I can have bus 2 there. and also you can individually scale. So if I wanted to have bus 1 at a different height, or I can actually do that. So if I want to make that smaller, I can bring that down, and I can also individually adjust, just highlight it, bus 2. Also, if you're clicking between the two buses, it will come up with a select control. So it's asking me now, because there's 3 items on the screen, do I want, disappears after a time, do I want D5, which means I'm now controlling my signal. So obviously I can scale that now. You see that, sorry, that's the position. The scale is this one. You see I'm scaling that up and down. If I want to select one of these, I can click anywhere on the screen. Should be able to. So just see. That's it. And I can now say, I think actually I must have clicked on that. I think I've got to be clicking in between them, or it's odd actually. Oh, okay, you've got to be clicking, I think, in between them. So it's now doesn't know which one, because I'm in the zone of 3 of them. So you can click on that and tell it which ones. If I want bus 2, it's on that. If I want, I think actually it's where how close you are to them, where it selects it. But alternatively, well, I don't normally use that actually as an option. Normally I would just click on these icons here, and also as you click on that, your colour dials change here, even in the software, which it does on the scope as well. So if I'm on bus 2, we've got white. If I'm on the channel there, which is blue for logic channels, you've got blue there. So instantly you can tell that this is your position for your for this. If you want to position your bus, you click on that, it goes white, and now your vertical position is there. I want to click on this bus, still white again because it's a bus, but I can position that, and I can also alter the scale vertically. And obviously the horizontal scale is altered by the time base, obviously. So if we bring the time base out, you'll see the full word data, and then the number, and then this is in hex. Here over the top here it's in ASCII, and obviously the scale here is altered, so they all alter at the same time. Let me go back to my trigger position there, and if I want to bring my scale back down to see more of my data, and if I wanted to start triggering at the beginning of it, let's just bring that in like that. If I want to trigger at the beginning instead of on a particular item, I would just go to trigger setup, and I would go to frame start. Start, close that down, just reset my horizontal position, which I've got set to left. You can obviously alter your horizontal position to left or middle. If I put it in the middle, then obviously my horizontal position's in the middle, but you can't see as much data because you're wasting the screen. So often I use my horizontal position on the left point here, so that way you can then bring more data across from the left to the right, so you're triggering on that point and you're running across to the right, obviously. So that's the decodes. You've also obviously got the tables, bus tables. So if I switch on bus tables, I can now bring this up, and I've got my 2 bus tables, one in hexadecimal on bus 2, and if I click on bus 1, then I've got it in ASCII format, so I'm showing it in ASCII format there. And obviously you can alter the scaling of that, which is quite nice. And if you want to get rid of the bus tables, you can either click on the bus table there to get rid of them, or if you've got them switched on, you can just switch them off by clicking on the X, and that will get rid of that. Okay, I wanted to have a quick look at how this decode, the logic decode, works when you're bringing in just say a square wave, just to show how clean this signal is and how it matches up with the analog channels. So I'll just set up for that now, and then we'll come back and have a look at see that we've got the logic channel in blue, which mirrors exactly. So if I switch off channel 1 for a moment, you can now see this is the same 1 megahertz square wave, and it's a beautifully square representation. But if I switch on, which is the main point of this, you can see that it's actually perfectly aligned with the analog signal. So the analog to digital seem to be perfectly aligned. If I look at the logic settings, what I've done is I've set a user level of 0 volts for the switching, so which is why we're centered, because obviously we're plus or minus 5, so I'm switching at 0, which is also where my center point is on my analog channel, so that's balanced. Now I've actually used these digital logic probes to measure signals up to 25 megahertz and with no problems at all. So if we bring up waveforms again, and we'll put this up to, oh, sorry, I didn't mean to do that, put this up to 2 megahertz. We're now looking at 2 megahertz, and you can still see that that's perfectly aligned if I change my time scale. And I'm triggering on my analog channel here. I could be triggering on my digital channel, so if I do that, so I'm triggering on a rising edge on channel 1, but I can also trigger on D7. So I'm now triggering on my digital channel, and my analog channel is still in phase because obviously they're both the same signal, but you can see that they match up beautifully. If I then go back into waveforms and ask for a 5 megahertz signal, now obviously this is not looking the greatest, but that's because it's just going through a very simple BNC, and the analog discovery really is about 5 megahertz is where it tops out. Anything above 5 megahertz, the waveforms are not great, and it is a cheap function generator, or relatively, because it does many other things as well, but that's not really the point of this exercise. The point of this exercise is to see how the digital logic probes compare to the analog channel, and they should obviously be the same, and they should be timed the same, and you can see there again that this waveform is following beautifully. If we change the time base on this and zoom in a bit to say 20 nanoseconds, it's a little more difficult to see on this waveform because obviously it's rounded here, but you can still see that the center point here is still running through roughly the center there and the center there. So that's pretty impressive, and that's at 20 nanoseconds. A little bit of jitter on that, but it's still at a 5 megahertz signal. That's still pretty impressive. I can go up to 10 megahertz. Let's just push that to 10 and see. That's going to be a bit more difficult to see now because the signal is so distorted coming out of the discovery. But the digital is still relatively good. If I bring that back out, time base wise, to say 80 nanoseconds, it's easier to see with that number that we're still through the center point, which is where we're switching on 0 volts. We are still basically spot on, and if we bring that in to say 10 nanoseconds, you can see that that's the center point, and we're pretty close on that. Getting a little bit of jitter on that edge, but that may even be the analog discovery. Also, of course, I've just got the clips on it. It's you know, the analog discovery it's got a BNC adapter, which I showed at the beginning of the video, but it's not really designed for giving out high frequency signals. If we just drop the analog discovery back to say 1 megahertz and bring this time base back down, which we can do that way, we can see how beautifully that matches. Bring this over a bit. Too far. There we go, we're triggering here, but you can see that we are absolutely spot on there through the center point. So I think that's quite impressive, the way that those two line up. And I've been using the logic probes, sorry, get rid of that. I've been using the logic probes for up to 25 megs, which I've been producing signals coming out of an FPGA and running 4 or 5 signals at 25 megs into the logic probes to analyze them, and I've had no problems with the logic analyzer on this scope at all. I think it's actually incredibly impressive. When you bring it out to there, you can see that it looks matching to the analog very accurately. And if we do a quick measure, you can see again they've got a 5 volt peak to peak with 1 megahertz. If we get rid of the quick measure, does of course drop out the logic channel. So as I go out of quick measure, which you can only do quick measure on 1 channel, then I've got to switch my logic back on again, and my logic channels are there. Obviously I can scale my logic channels. There's quite a lot of, as I did previously, there's quite a lot of features on that, so I can actually scale my logic channel, so you can see that I'm scaling it down. But obviously if I scale it to the same scale, then you can see that the top and bottom are matching almost perfectly with that, as are the side of the waveform, which is where it's switching off through the center point here, because that's obviously the center of the analog channel 1. That's the marker for the digital channel, which always marks actually at the bottom of the channel, I believe. Yeah, it always that mark is always at the bottom of the channel, as opposed to the center point on the analog channel, which is why those are offset. But fundamentally they both match, and that I've discovered recently when I've been using it for FPGA work, that the logic analyzer on this scope is extremely impressive. But I think there's quite a lot of electronics inside the logic probes, and as I said to you, even the actual wires are not just wires, they've got resistors in them, as does a normal analog 10-to-1 logic probe. For capacitive coupling, etc., so that effectively the signals that come through that logic probe are extremely clean, which is shown by the fact that the logic protocol analyzer worked perfectly, and of course that wouldn't work perfectly if the signals that it got to begin with were poor. I think I'm going to stop the video today here, but for the next video what I intend to do is I'm going to have a look at a thing called a microprocessor, which is something I bought myself at Christmas as a sort of Christmas present, which is a 6502 microcomputer sort of development kit that comes from the 1980s, but I was using that about a week ago to have a look at the signals coming out of that, and using the logic analyzer on that, because that device runs at 3.5 megs, the main processor, but it's actually halved, and there's chips inside where they use I can't remember what the name of the chip is, but they use a chip to reduce the frequency to half. Name escapes me, but we'll have a look at that in the next video. But for today I think I'll leave it at that. I hope this video has been useful. I apologise if I haven't been quite with it at the moment. I've got a bit of a cold, which you might be able to hear, probably from the fact that in the UK at the moment we're experiencing weather down to sort of -3, -4, so a lot of people have got colds, etc. So I've not been thinking that clearly, so if I seemed a bit subdued in this video, I apologise. I just wanted to get another video out, as it's been a few weeks since my last one, but hopefully I'll be back within a week or so with another video, and I hope this one's been useful, just to show the logic analyzer and the protocol decode on the RTB2004, and hope everybody's enjoyed that, and we'll see you on the next video.